Hey everyone, Dev here. For those of you who don't know, The Witcher 3 has this mini game in it called Gwent. It's a card game. In this video, we're going to go through how to scan and find the values for the Gwent score, which is pretty straightforward, but there's some subtleties to actually getting it to work, and that's what we're going to go over today. So to start, I've got The Witcher 3 queued up here. At this point, we're ready to start scanning. The tricky thing about Gwent is that it's not a constant thing in memory. So you'll find that even if you scan and find the right values, once the game's over, the memory values will be freed. The game itself is it's dynamically created. It's dynamically instantiated in the game and has its own entity object that has the score as just one part of that. There's a lot more to dig into, but we're just going to cover the game itself and finding how to win. But what I want to do is just to get the score up as much as I can, only focus on having scorecards, which is nice. Here I don't have any cards that would say like change the conditions on the map. If you don't really know Gwent, it's not really important, but suffice to say, I just want to focus on getting cards that will change the value that I want to look for. So round starts, my turn. So I start with a score of 0. Now, normally I don't like scanning for zeros because there's a lot of zeros you'll find in memory, but in this case, because the game is so short, you want to get as many scans in as you can. So what I found, again, through trial and error, I initially thought that maybe it might be a 2 byte value because the scores can't really be that high. They actually used a 4 byte value. Just in general, when you're looking for scores in a game, you're going to see integer values, which are usually 4 bytes. You're not going to see floats often because it doesn't need that precision unless you're dealing with division. In that case, floats are almost guaranteed. But in this case, it's 4 bytes. So we're going to scan for our score. And I like to pause the game while scanning, especially when you'll see at the end of every time I place a card, it will go to the opponent's turn, and I want to make sure that I get the scan completed before they do something which could affect my score. First scan is for zeros. By default, Cheat Engine actually, I believe, only looks at writable memory. I like looking at both readable and writable in case there's some kind of global values that it might be using, but it just gives more surface area to scan. So scan. You're going to get a whole bunch of results because, like I said, there's a lot of zeros in memory. Next thing I'm going to do is play a card that gives me a score. I like to play scores if I can. I like to get numbers that are not something that like you can multiply 4 to get to. So it's not doesn't divide by 4 or anything. In this case, I'll use 5. 5 is actually a little easier to find, a little more unique. But the reason I do that is because you're going to see a lot of things that are multiples of 4. So I'm going to use 5. There we go, and immediately jump back over to Cheat Engine, scan for 5. And see how it goes to the opponent's turn. I want to make sure I pause the game so that they can't play anything to affect the score before I can do anything with it. Okay, so here's all the values that are 5. Let's see, they have 5 now too. I'm going to place a 6 to get another odd number here. And quickly go over and change this to 11. 0. This happens. Sometimes it will actually not update. Like there's a space between your turn and their turn where it'll finish the update. So this has happened many times to me. It's okay. We can still do this quick enough that we can find the score. So do first scan, look for 6. That's why. So it looks like the AI probably had already, this is the tricky part that I was mentioning, where you got to catch it before they can do anything to affect your score. I didn't catch it fast enough. They had already, in the game, in the memory, it had already changed my score, probably based on their predictive algorithm for the AI here. So let's set this back to 6. All right, first scan, look for 6. So in the future, what I should have done is done undo scan so I can go back and then scan for the new number. But the nice thing is because I'm not starting with 0, I have much fewer starting results. So I'll play this card that clears up the rain values. You don't need to really worry about it. Either way, what you need to know is it should change my score again. So I'm going to wait for their turn to finish this time because they could play something that affects my score, just like that. Okay, 18. Great, so there's a bunch of 18 values. Now, I'm going to go down further because I know this goes down further. Yeah, see, there's a bunch. So let's even just we'll go unchanged value, 18. There's these 3. Okay, should be good enough, but I know just from experience that I can get this down even further. Let's throw out, I don't know, it doesn't really matter. Sure, 23. Okay, so these 2 are what we're looking at. Okay, So what we're going to do now that we've isolated where it affects our, see, like they affected our score again. That's what makes this one particularly tricky. Well, one of the things. You have two values here. Okay. Now, oftentimes when you're doing scans, as you probably know, one may be just a display value, the other one might be the true value. So what we're going to do is we're going to look at both. There's only two. It's really easy to do this, but we want to look at what axis is it. So this is reads and writes. So 6, 8 is the top one, 20 is the bottom one. Let's see what axis is this as we play the game. Okay, so let's play a card here. Great. Okay, so there we had a bunch of axes. This was less, so 8 and 1. So there's an interesting thing to note here is that you'll see this only did a one read. So this is a write into some value. Anytime you're looking at, so the value in memory is ultimately the ultimate source of what you're looking at, of what's going to be used in the game. Any registers are just temporary. So reads come from memory like this. It's a memory address, it's a pointer. Writes go to that address. But immediately I see down here, anytime I see a structure like this in an instruction, where it's like some value plus something times something else, that tells me that it's in some kind of array-like structure, which is usually how a game engine will store data with other directly related data, like two sets of scores, for example. What this means is this is the first one is the base address, the second one is the offset into that address, and this third value is the size of the whatever value you're looking at. So in this case, the base address is just like an entity object pointer. It's likely an entity object, in this case it is. The offset is the first one, and then this is the size, which is in this case just like a 4-byte integer, which is what we're looking at. So I know that that's usually what you're going to be finding, especially in games, when you're looking at the data structures that are critical to some data you're looking for. So in this case, interestingly, there's 33 and 6. Don't be thrown off by the number of times it's accessed. This is kind of what threw me here too, is I was looking for, I was following this for the longest time because I'm like, oh, well, there should really only be one source of the data itself, right? There should only be one definitive source of that, whatever value we're looking for. But what can often happen in games, especially when you're dealing with like opponent AI like this, is that they may the value you're looking at may be written and accessed by multiple places, and that's normal, not just in display values, right? So there could be values where the AI is, assessing a bunch of different things it's going to try, and so it reads it a whole bunch of times like this. It may be written from, an accumulation of these different parts of the score to create this final score. So there's a bunch of different reasons for it. Don't be thrown by seeing more than like multiple times where it's read from or written to. I followed this rabbit hole for quite a while before realizing that it wasn't the right value. So I know just from experience that this is kind of where we're looking at, but also just for the reasons I gave, this is where you want to start just in case. So where this is the read and this is the write. We can if we want to affect every score that reads from it, we want to affect the original read. So if I go to show disassembler, I'm going to see, now I have this marked here because of the time that I've spent looking at this, but I know that this is the write to the value, but what you want to do to test this is try noping this. So replace it with code that does nothing and see if it changes anything. Now, I'm not going to go ahead and do this, but you could, if you want, look at the address like this and change this. What you'll find is, so the one we wanted is not 6.8, it's 20. If you change this, because it's being written from and read from and written to so many different times, you changing it may just be overwritten in another instruction. I know that's what happens here. I can maybe show you. Let's see what happens. Again, I did a nope here. I'm going to revert this back just to show you. So changing it to 45, our score, it doesn't change immediately. Sometimes it waits until after the instruction goes. But look, it went to 0. Okay, so me changing it did nothing. However, if I go in here, and this is the instruction that we found was writing to that address, I'm going to try replacing it with code that does nothing, and we'll see what happens. So let's try playing a card. Cool. So we know that we found the right value. It appears that way. However, when they play a card, you'll see their score also doesn't get updated either. So what that means is that this is a shared instruction, at least to those two places. It may be more, but it's not going to be as easy as us just modifying this instruction to just add whatever score we want to the game. Instead, what we're going to be doing is, let's take a look at, I'm going to revert this back. I want to see what instructions this accesses, or what addresses it accesses. So let's play through it and we'll see exactly where this code is writing to and what different addresses those are. So let's just throw this out here. Cool. Okay, so there we have a bunch of different values. 9 and 2, that's our scores right now. 9 and 7. Great. So now we know these are our two scores, and these are the only two that are being written to. No matter what else I do, these are the only two being written to. Great. 10 times exactly the same amount. That's wonderful. So we now know, and see how the value difference here is 0 and 4. So there's literally a 4-byte difference between them. That means that aligns with our initial, where did it go? Analysis of seeing that this is a data structure here. And they are right next to each other in that data structure. Awesome. So the next thing we want to do, now that we've found that it accesses multiple instructions just as we thought from noping it, we saw that it now it was affecting both scores. We want to find a way of differentiating between these two so that we can write code to overwrite it and affect only our score. So what you can do is, and I know this hasn't been working, but I'm just going to try just to show you, is you want to try to find what commonalities there are between them. So you can look for a unique identifier, some kind of unique identifier to differentiate it between the two values, so that when we write the assembly code to overwrite it, we only write for our score. So we need to find an identifier for our score. And we're going to change this to because I didn't mark anything else by default, it'll set it as this, but I'm just going to be explicit here, and now we have the two different groups. And let's go find commonality between addresses. Great. In this case, for some reason, it only found a commonality. It only looked at this register, which is weird. Not sure exactly why that is, but stack pointer is useless to us because it's going to be the same likely as because it's accessed from the same spot. It might be different, but stack pointer is not a register we want to look at for an identifier. So instead, what we can do is we can manually just go show register states for the first one. So that's our score right here. And show register states, and this is where the opponent's score was being updated. Okay, so let's look at these ones. You can always potentially look at the stack view and then the floating point registers, which is like XMM0 through I can't remember the highest number, 15 here, in 64-bit Windows. But we don't need to do that yet. Let's start down here. Okay, so looking through these different values, this is the score. Great, that's what's being written. That was in the instruction anyways. These are a bunch of pointers, or appears to be pointers. This R10 is the same, so we can't use this to compare between them. Pointers, same values. 0, okay, nothing in R14 are the same. Oh wait, look at this. R15, a 0 and a 1. Anytime you see a low value like that is in a data structure and they're different between two similar data structures, that's how you can be sure that's a good identifier, because 0 and 1 is is easy enough to compare, but also usually when they're only one apart like that or close like that, there's some kind of ID value. So we're going to try using this value here in R15 to differentiate between the opponent's score and our score when we're modifying the assembly. So let's go into that, what that looks like. Now, I've gone ahead and already, we can get rid of all this stuff. We know this is the instruction here. I've already gone ahead and created a script to do this, but I will show you kind of how to get started first. And you're going to want to, go to Tools, Auto Assemble, and you're going to create a AOB injection. This, I think most of you know what this does, but it scans for an array of bytes, which is unique in code, to find this instruction in memory. I'll just call it injects. I'm not going to use this one. Great. So it's looking for this unique array of bytes, and then it'll do an injection there. Here's the script. Here's what the script looks like for automatically winning in Gwent. So this is normally what you use. I usually get rid of this and instead do some manual things instead of doing a scan across all of my memory to look for this array of bytes, which in many cases I've found actually isn't unique, especially with larger, more complex code bases. instead, what I do, especially for a game that doesn't update often, and like Witcher 3 in this case it's not getting any more updates because it's a few years old. Still relatively new, but it's not seeing any updates. Even still, I can always use this to reference this to look for the array of bytes and scan later on if I need to update it. What I do instead is I assert that at this point here, which if you look in my instructions, this is the offset into the module in memory, which is doesn't care. ASLR is irrelevant for this because this section is always at the same offset. I'm doing an assertion at the very top of my code that at this value, which is here, this memory address, these bytes exist, which is the instruction that we have here. So what that means is making sure that like I'm changing the right bytes before later going on. Actually, I should probably do it to this because I'm going to be changing that. I'll do that later. But regardless, I'm checking to see if these bytes exist. If these bytes exist there, then I know that I have the right instruction and I can move forward with my code. If this fails, then the rest of it won't work. And then I go forward and I want to define, this is just makes it easier for me to reference this address every time. Instead of typing witcher3.exe plus 155 6d32, I just call it function underscore Gwent score update. The naming format doesn't really matter, but this just allows me to reference this offset with just this simple name. And then I register it as a symbol just so that I can easily see it in the disassembler when I'm changing this code. Then I go and allocate an area called new mem, which is kind of standard in Cheat Engine. That's kind of, I think, the default you get. It's just a new memory location, 4,000 bytes, which is probably overkill, but it's the default page size in Windows, so you're not going to really get any shorter than that, any smaller than that when you do this, at this address. And I can probably just, instead of using this, I can just reference fn Gwent score update, but this works too. And I go and register the symbol for new mem. What register symbol does, if you don't know, is it makes it so that this symbol here, this label, literally new mem, and in this case fn underscore Gwent score update, are now visible by anything else in the program. So that means across different Cheat Engine scripts. It also means within the actual memory viewer too. And any other memory viewers. If you're using x64dbg and you load symbols, or you're using reclass.net and you click load symbols, you'll see the symbol for this in the code. And I'll show you what that looks like when I actually run this. Okay, so now you have labels. Labels are local in Cheat Engine. I can't reference them outside of the script, and it doesn't really. But what that means is I can just use these as quick little easy ways to separate my code within this script. So there's all my labels. Here's the meat of what this actually does. So here's the original disassembly where it originally was. And so you'll see I've used a function Gwent score update that references this particular location within like that offset within memory. And it's basically setting this to be these instructions. Okay, jump new mem, then num3. The reason why I do that is because jump new mem is actually 5 bytes if you actually defined it as like the bytes for the instructions themselves instead of the opcodes. You have 5 bytes, and then I need another 3 because I'm going to overwrite 8. 1, 2, 3, 4, 5, 6, 7, 8 bytes. There's the original score. So when I enable this, it's going to change the original code to this, and there's a label for return right after it, which, because there's no jump after this is just also a part of the original disassembly that's being replaced here. Okay, so what I want to do, this is going to basically jump to this location, which is a symbol, which means that I can access it from within any other script, anywhere in the assembly while it's active. We're jumping to it. This is where the meat of all of the changes are going to happen. First thing I'm going to do, and this is something that I haven't seen covered in a lot of other Cheat Engine videos, but it's just good practice, is anytime you're doing some kind of compare or any other assembly instruction that modifies the E flags, you're going to want to push them to the stack so that you can pop them out after in case there's instructions that come directly after your modification that need to use those E flags for some kind of jumps, for example, like conditional jumps. So just as good practice, if you're doing a compare instruction or any other assembly instruction that modifies those flags, you're going to want to push the flags at the beginning, and then you'll see at the end, where do I do it? Pop F right here. I'm going to pop the flags back from the stack into the flag registers. Okay, so first thing I'm doing, as we saw, if you remember, R15 was where the identifier was. 0 was our identifier, 1 was the identifier for the opponent. So I'm going to compare it, hex 0 here, to R15. And if it's 0, we're updating our player score. Now, you don't have to do these jumps. There's lots of different ways you can go about like actually structuring a code. But this is just kind of like the top, and it should, for me, it just allows me to understand, okay, if it's 0, I'm going to update player score. If it's not, which is anything else, it's going to update opponent score. You can be more explicit and say if it's like compare it to 1 if you want, but this is just, this just works. So if it's 0, we're updating our player score, and here's what we're doing. Now, you'll see here's the original code. It's actually these. You'll see down here. In the original code, it's adding EAX to this data structure, which is where our code exists. What we're going to do is we're going to, instead of adding from the EAX register into that code, that offset in memory, like this actual structure, we're going to add the 200. Now in Cheat Engine, 200 is sorry, you can easily add an integer value by using the number sign. You could easily also add hex by just making it whatever you wanted. So like if you want, I don't know, 32, you can do this. But I'm just doing this just to set it to 200. Adding 200 into our score location, and then jumping back to original code, which is going to complete the original instruction that we overwrote, which is this. And then I got rid of this comment because I'm doing this in my own code, but just modifying it. Pop the flags back from the stack onto the E flags, and then go back to return, which is the instruction directly after our jump and nope. So that should be right here. Sorry, yeah, right here, because we overwrote these two instructions here. Going back up, if the R15 is not 0, it's going to update opponent score, which is basically just the original code. You can change this to 0 if you want to like always have the opponent, if you want to beat them 200-0 every time, or just in case they could get over 200, you want to make sure that they can't, just set it to 0. That's fine. Totally up to you how you want to modify it. You can do whatever you want now that you have the unique identifier and the actual data structure. This is just what I did, and it works so far. And then just like the other one, it's going to jump back to original code, which is afterwards. Sorry, it's right here. It's going to do the next step, and then popping the flags back in case there's any other instructions right after. In this case, I don't think there are, but oh yeah, there are. There's a and a compare, but it's just good practice to do that in case there's any other instructions immediately afterwards that rely on the E flag state. And then jump to return, which is right after the original, the overwritten assembly instructions. So that's once we enable it, it's going to do that, which should set our score to 200 every time it's written to, and just leave the opponent's score to whatever it was supposed to be set to. And then when it's disabled, we're just going to basically write back these bytes that we overwrote with this original code, what we wrote here. Sorry, what we wrote here. So there's 6 bytes here that we overwrote. And then unregister these symbols. It's very important that you do this. Otherwise, it's going to just mess up what you have in memory. Because we define these symbols, which they're globally accessible across anything that's accessing this in memory that's using symbols. Again, that's like reclass.net, any other debugger, anything else that's accessing it. And deallocate new mem, which is the region that we allocated to store these instructions to jump to. And that's it. So that's how this script works. Let's actually see it in action. First, I have it right here. That's where I saved it. If you watch, I just click, and you'll now see in here the symbol that we defined, which is function Gwent score update, and it's just jumping to new mem and then doing a nope of the nope. So it's interesting. This is Cheat Engine. This nope 3 is not actually like real assembly, I don't believe. This is just Cheat Engine allowing you to quickly do a nope with 3 bytes. If you go and look it up, it's really interesting. There's actually a way of there's specific instructions that you'll see for noping out from anywhere from like, a nope, which is 1 byte, all the way to something like 63 bits, I guess, because I think that's it, because you don't want to mess up with alignment, and that's a whole other topic. But things that are page aligned, you don't want to mess with that for a bunch of reasons. I won't get into it. Regardless, I don't think this is a true assembly instruction. This is just a Cheat Engine thing. But we did a nope for 3 bytes, which you are seeing right here. And if we jump to new mem, you'll see here's my instructions that I wrote with some complicated jumps, which are just basically what I did here. And then it pops it and jumps back to here, which is right after we finish the note. So now that that's actually active, as you can see, let's play some Gwent and see what happens. So score isn't updated now. That's normally happens because there has been no writes. There's been no access to that instruction yet. But when I play a card, oh look, I have a score of 200. Let's see what happens when the opponent plays. Okay, they're going to play 4. Their score stays updating whatever it wants to update. Even if I play another card that should give me more points, it stays at 200 because that's the instruction that I chose. Oh, what did I play? Okay, here we go. Cool. Doesn't matter what cards I play. So now what I'm going to do, the opponent won't know what to do. They have 6 cards left. I'm just going to skip. And it's fun seeing how it messes with the opponent's AI. But they're basically going to try to just play every card. The interesting thing is when I was looking into this is kind of maybe just a side note on Witcher 3. What I noticed is that the opponent was accessing the score quite often, and what I believe that is it's basically trying to play different cards in its hands to see what score update would be. So it doesn't seem to be a particularly complex decision tree or AI for the opponent here. It's just simply looking at what score would happen and how it would affect it in the next one. I could be wrong, but I believe that appears to be what was happening. I want to dig more into it, but that'll be another time. And in this case, I won with a score of 200, which is ludicrous. And there we go.
I really hope you enjoyed this video. Again, guidedhacking.com/donate, patreon.com/guidedhacking. Please support us so that we can continue to make videos, and peace out.